Newton's method is a way for finding the roots of an equation. Of course, if we have a quadratic equation, we simply factor it and find the roots. And if it's a cubic or a quartic, there are complicated formulas that we can use for solving them. However, once we get higher than degrees 5 or 6, let's say, we don't have a way to solve those. So, for example, if I asked you to solve something like 48x bracket 1 plus x to the power of 60 minus 1 plus x to the power of 6 plus 1 is equal to 0, even some of your calculators are going to have difficulty finding the solution to that. So when we come across those kinds of problems, we use a method called Newton's method. It gives us an approximation for the root, and we continue the approximation until we get the desired number of decimals of accuracy that we need. So here's the method. If x1 is the first approximation to a root of this equation, f at x is equal to 0, then successive approximations are given by this recursive formula. X sub n plus 1 is equal to x sub n minus the function at x sub n over the derivative at x sub n, where n is an integer, 1, 2, 3, etc. Provided that the derivative at that point is not 0. Let me give you a quick sketch so you have a picture of what we're doing before we get started. Okay, so here's a function, or a part of a function. I'm going to call this function f at x. Then we can see on the graph that that's the root of the equation. And our goal is to find out what that root is. Of course, the coordinates of that root are y is equal to 0. We're trying to solve for that x value. So here's what we do to start, is we choose a point that we think is the root, and we're going to call this point x1. Then going up to the curve, this coordinates of this point are x1, and the y coordinate would be the value of the function at x1. So we're not going to write x1, y1, we're going to write x1 and the function at x1. Then what we do is this. We draw a tangent line to this curve at this point. I didn't mean it to be this good. And this is what we call x2. The coordinates of that point, x2 and 0. And so then this is our second approximation to the root. How do we find this point x2? Well, we write the equation for this tangent line. That is, y is equal to m x minus x naught plus y naught. What are we using for our x naught, y naught? Well, we're using this point, x1, and for y naught, the function at x1. What's the slope of this line? Well, the slope of this line is the derivative at this point. So the equation for this line can be simplified or maybe complicated by writing it this way. F prime at x1 times x minus x1 plus the function at x1. So the equation for this line right here. Then if I want to know the x value, the x2, where this crosses the y-axis, then I'm going to substitute in this point here. Y is 0, f prime at x1. X is x2 minus x1 plus the function at x1. And then we solve this for x sub 2. That is, subtract f at x1 from both sides, divide by f prime at x1, and then add the x1 over. That's where this equation is coming from. So once again, we're going to, I'll show you in 2 steps right over here. We're going to subtract the function at x1 equals f prime at x1 times x2 minus x1 plus, oh, got it, moved it over already. Okay, then I'm trying to isolate the x2. I'm going to divide by f prime. So I have negative f at x1 divided by f prime at x1 is equal to x2 minus x1. I'm going to add the x1 over to that side. That's how I get x2. And then I keep on going with that process until I'm close enough to the root. So that's where this xn plus 1 is equal to xn, subtract the function at xn over the derivative at x1.